I suppose I should warn you now that the concept of continuity is not a difficult one, but I feel like things can get kind of dense here, so just heads up on that, right? Make sure you've got your brain turned on for this one. Um, Saying that a function is continuous, like in plain English, means that it doesn't have holes, it doesn't have jumps, it doesn't have asymptotes. Basically, it's one of those functions that you can draw like using your pencil without taking your pencil off the paper. So if it's got a hole, it's not continuous. If it has an asymptote, not continuous. If there's a jump, it's not continuous, right? But in this lesson, I really need to talk about what it means formally, like what the math behind it means. So some stuff is going to pop up on the screen. It may be scary, but I'll walk you through it. Right. The definition, there's two definitions to work with, right? The first is we say that a function is continuous at x equals c. So in other words, we can say that a function is continuous at one specific x value if there are sort of two statements that are true, right? First of all, the limit has to exist as x approaches c. So that limit needs to exist and it needs to be L. The second thing is f of c has to be L. In other words, when you actually plug c into the f function, you also need to get back L. And this should make sense, right? What this first statement here says is it says, hey, you've got a function, and as you get closer and closer to c, the two sides of the function are meeting up at a height of L. It's saying, yay, at least the two sides are coming together. Then the second statement is saying, hey, and by the way, when you plug in c, when this is your input, L will be your output. In other words, that spot right there where there might have been a hole, nope, it's filled in, right? In order for a function to be continuous at a point, these two things have to be true. In fact, saying that the function is continuous at c is the same thing as saying these two statements. So those two things can be swapped out for one another. Okay? So that's the definition of a function being continuous at a point. Right? So what does it mean if we say that a function is generally continuous? So you say, oh yeah, by the way, f of x is continuous. Well, it means that it's continuous for every single x value on its domain or on the interval, right? So we can say that a function is continuous at a value, or we can just say, hey, f of x is continuous. So as a very simple example, I could ask, is f of x equals x squared continuous? The answer is yes, absolutely, right? It's a parabola, right? It looks like this. There are no holes, there are no jumps, there are no asymptotes. Because all of those things are true, the function is continuous everywhere. And because it's continuous, it means these two things are true at every point, at every x value of this function. Okay? So that's what it means to be continuous. So the next thing I should talk about then is, so how do we determine if a function is continuous at a particular input value? And a part of that goes back to, we'll just do those two things on the previous page, but in case you need steps, in case steps are helpful to you, here they are, right? As far as I'm concerned, your steps are this. First, determine if the limit exists, right? Side note, if it's a piecewise function, you probably need to think about one-sided limits. You need to look at the limit from the left and the limit from the right. For a more normal function, you can follow our standard procedure of attempt to evaluate the expression for the value, sort of work through that limit, right? If that limit exists, great, keep going. If that limit doesn't exist, then there's no way the function is going to be continuous. Like think about that. If the limit doesn't exist, it means the two sides didn't meet, which means I don't even care what happens at that value, right? So after we find out if the limit exists, our next step is find out what the value of the function is at that input value. In other words, actually plug in the value, right? The last thing you need to check is this function will be continuous at that value only if those two things exist and are equal to one another, right? So the short of it is, find out if the limit exists, find out what the value of the function is. If they're the same, it's continuous. If they're not, it's not continuous. Simple as that. So here's my first example. I want us to determine if this function is continuous at x equals 7. And so what I'm going to ask you to do is I'm going to ask you to go through and sort of do those two things, right? On the one hand, find the limit as x approaches 7. On the other hand, find out what f of 7 is. So pause the video, do that for yourselves. So in order to take this limit, we were supposed to always attempt to plug in the value because, hey, it might work, right? When I attempt to evaluate for 7, I end up with 49 minus 35 minus 14 over 14 minus 14. That gives me 0 over 0. Surprise, surprise, try harder, I'll move on. right? I'm going to use factoring this time, so the limit as x approaches 7. I get x minus 7 in the numerator and x plus 2 as well. In the denominator, I could factor out just a 2. I'm actually going to factor out a negative 2. Doing that gives me x minus 7. You may have taken an extra step for that. That's fine. When I do that, I notice that these both have an x minus 7, and all I have left is this x plus 2 over negative 2. So now I will attempt to evaluate again using x equals 7, and when I plug that in, I end up with 9 in the numerator, negative 2 in the denominator. So that's what I got for my value. Rather, that's what I got for my limit. This is my limit. Okay. Now, what about when I actually try to do f of 7? What happens when I plug 7 into this function? Well, when I plug it in, I end up with 0 over 0. And 0 over 0 is undefined. Now, you may be thinking, oh yeah, but over here I can just cancel them out. That works for the limit. And the reason, just to give you more of a sense of it, the reason is the limit doesn't care what happens at 7. The limit is simply saying, as I get close to 7, this is what I am approaching. Right? When I actually try to plug 7 in, I get division by 0, which is like a crazy explosion, right? Okay, so in the end, what does this mean? This means this function is not continuous. Not continuous at x equals 7. The limit existed, but the value of the function did not even exist, and it certainly wasn't the same. Because of that, not continuous. And that's all we need to say at the moment. So I have one more example for us to look at. Determine if this function is continuous at x equals 3. Right, so same deal. You're going to need to go through and follow the same procedure we did in the previous problem. So pause the video and work that out on your own. So in order to find the limit as x approaches 3 of f of x, I'm going to need to do two one-sided limits. First, I'm going to have to do the limit as x approaches 3 from the left, and I'm also going to have to do the limit as x approaches 3 from the right. Okay? So as I approach 3 from the left, well, from the left, it means I'm using values that are less than 3, so I'm going to use this function. So instead of writing f of x, I'm just going to write the part of the function that I'm using, 2x minus 1. Right? When I attempt to evaluate with 3 there, I'm going to end up with 6 minus 1, which is 5. Oops, might as well use red for that, 5. Okay. On the other hand, when I'm doing the limit as x approaches 3 from the right, means I'm using values that are larger than 3, so I'll be using this portion of the piecewise function. So x squared minus 2x plus 2. So as I do with all of my limits, I attempt to evaluate for the value of x. That's this 3. Sorry about that x over there. This gives me 9 minus 6 plus 2. This is going to give me 3 plus 2, which is 5. Because these two things are the same, what does it mean? Right? This means that my limit as x approaches 3 of f of x is 5. So that means the limit approaches. Now all I have to do, I don't have a lot of space, is I need to figure out what is f of 3. Right? So when I take 3 and I actually plug it in to this function, what do I get? Well, it's interesting. You'll notice neither one of these actually says less than or equal to 3 or greater than or equal to 3. So because of that, f of 3 is actually undefined. And so what does that mean? That means that once again this function is not continuous at x equals 3. Now, let's take a brief trip into what if land. Right? What if this had been greater than or equal to? Right? In that case, what would f of 3 have been? Well, because this now says greater than or equal to 3, I can plug 3 into that one. And when I do evaluate that one for 3, I'm going to get 5 again. In this case, the limit would be the same as the value of the function, which means the function would be continuous at 3. So as this problem was originally written, it's not continuous. If the problem had greater than or equal to 3 on it, then it would have been continuous. I wanted to sort of give you guys a chance to see both of them at once, so I hope that was clear. Now, I might throw out one other question. This question only asked if it was continuous at x equals 3. I might ask, is there any other place where the continuity might have been in question? And right now I'm kind of getting into the next lesson without really officially doing it, but it's sort of a fair question. is there anywhere else that this function might be discontinuous? Well, discontinuous means it would have holes or jumps or asymptotes. And in a piecewise function, that's probably only going to happen at the jump. In fact, if you think about it, 2x minus 1, what does 2x minus 1 look like? Like, pause the video and think about that. 2x minus 1 is a line. Like 2x minus 1, it's like a slope 2 line. There are no holes, there are no jumps, there are no asymptotes. That part's fine. Right? X squared minus 2x plus 2, nice mild-mannered parabola. Nothing wrong with it. Right? There's nothing wrong with this part of the function, nothing wrong with this part of the function. The only place there might have been discontinuity was right here. So if those match up, it means the whole function's continuous. Okay? So I'm going to be talking a little bit more about that in the upcoming video. I'll see you there.